All right, welcome back. It is time for another day of Advent of Code. We've made it to day 20 now. Um, After these last couple of days, it's this one was pretty straightforward, I think. Didn't take very long. Um, so yeah, let's dive right in. Boop. All right, day 20, Grove Positioning System. It is finally time to meet back up with the elves. When you try to contact them, however, you get no reply. Perhaps you're out of range? You know they're headed to the grove where the starfruit grows. Starfruit grows, so if you can figure out where that is, you should be able to meet back up with them. Fortunately, your handheld device has a file, which is your puzzle input, that contains the grove's coordinates. Unfortunately, the file is encrypted, just in case the device were to fall into the wrong hands. Maybe you can decrypt it. When you were still at the camp, you overheard some elves talking about coordinate file encryption. The main operation involved in decrypting the file is called mixing. The encrypted file is a list of numbers. To mix the file, move each number forward or backward in the file a number of positions equal to the value of the number being moved. The list is circular, so moving a number off one end of the list wraps back around to the other end as if the ends were connected. For example, to move 1 in a sequence like 4, 5, 6, 1, 7, 8, 9, the 1 moves 1 position forward and lands here between 7 and 8 instead of between 6 and 7. To move the -2 in a sequence like 4, -2, 5, 6, 7, 8, 9, the -2 moves 2 positions backward, wrapping around, landing here between 8 and 9. The numbers should be moved in the order they originally appear in the encrypted file. Numbers moving around during the mixing process do not change the order in which the numbers are moved. Consider this encrypted file. And then we have 1, 2, -3, 3, -2, 0, and 4. And then we can see here how they move. So this is how they start out. And first we deal with the 1, which get moved over 1. Then we have to deal with the 2, which is now over here and moves forward 2, so it lands here between -2 and 0, right here. 2 moves between yeah, so the 2 moves 2 over, right? That's where it is right now. Sorry, got confused. So this 2 moves 2 over, so that's 1, 2, so it lands between -3 and 3. That's right here. The next one is -3, which is right here right now. So that moves 3 to the left. So that means it goes 1, 2, 3. So it lands between -2 and 0. And the next one is 3, which is currently here. And it moves 3 over, so 1, 2, 3. And you can see it landed there. And then it's -2, which is currently here. And this is where I missed this, reading it through. So you can see -2 is supposed to move 2 to the left. And notice that moving 1 and then another, it doesn't land in the first place here. It ends up at the end. So anything that moves left apparently cannot end up on the first position here. And similarly, anything that's moving to the right cannot end up on the end here, but rather ends up in the beginning of the line. 0 doesn't move, and 4 moves between -3 and 0. Yep. Okay. So then the grove coordinates can be found by looking at the 1,000th, 2,000th, and 3,000th numbers after the value 0, wrapping around the list as necessary. In the above example, the 1,000th number after 0 is 4, this one is -3, and the 3000th is 2. Adding these together produces 3. So now we have to mix our encrypted file exactly once. And what is the sum of the 3 numbers that form the Grove coordinates? Let's take a look. All right. So we have our part A right here. It just calls do stuff. And as usual, do stuff involves loading all the lines, and then usually there's some parsing, but this one was so simple that I didn't have a separate function for that. They were just the input is just a list of numbers, or the real input is also a list of numbers, a lot more than 5,000, but they're just numbers, so there wasn't really a lot to do in terms of parsing them. So we create a list that has all the numbers in the order that they appear in the file. You ignore this multiplier. That's something for part B. For now, we just parse them as integers and store them in this array of the original order. Then we create the current order, which is a list with enumerated elements from the original order. So we've used enumerate a couple of times before during the Advent of Code 2022. Basically, what it does is it returns. So if you have an input that looks like something like that, the output of why am I doing that? Let's just do it like this. Much easier. Okay, so we have our list, which is just some numbers, right? Doesn't matter a whole bunch. And if we enumerate those, we get the same number of elements, so 4 of them, but each one of them is turned into a tuple where the first element is an index and the second element is the element from the list. And the reason we do that is because we need to be able to identify the numbers as they appear in the original file. I kind of got tripped up a little bit because I used the test input and I just stored them as integers, and then I went through them. I went through the original order and found the element, and then I would call .index on current order to find just that value. But it turns out that in the real input, we can see that let's say input, no, data input. So what I'm doing here is I just sorts the input. I can show you what that does. No, sorry. Well, it doesn't really matter for now, but numeric. So that sorts it. And then we have something called unique. Unique shows, removes duplicate lines that are like right after each other. So that's why we have to sort it first. Then we pass it through unique. -C counts how many there were of each. And then we sort it again. And then we can see that a lot of these values appear multiple times. Like 407, for instance, appears 6 times. -8,677 appears 6 times, and so on. So yeah, the values are not unique, and that's why we had to add this enumerate thing, so that when we're going through the original list, we make sure that we are actually acting on the correct instance of 407 in the current order. So that's what we're doing here. Okay, so again, this rounds thing is a part B thing, so ignore that for now. It's it's just going to be 1 in part A. So we don't need to worry about this loop right here. So what we do here is we go through the elements in the original order, enumerated in original order. And then we call shift on it, which is a function that we will look at in a second, and that returns the new order that they are in. And then we do that for every single element, and eventually, once we're done with that, we have them in the right order. So that once this loop is complete, that we've done one full round of mixing, and then we have to find the value 0, remember, because that's where we have to start counting 1,000, 2,000, and 3,000 ahead to find the values that we need. So we go through the current order array or list, and if we find the value 0, then we break out, and then we have our IDX pointing to that value. And then it's a simple matter of calling sum on these 3 values. So let's take a quick look at this shift function. It takes the current order and an element. And remember, an element is a tuple with 2 elements in it. The first represents the original index of it, and the second element is the value that we found in the input. So we get the current index, and we can call index on it because they are each instance of each time 407 appears in the original input, they're going to have a different first element in that tuple that we're passing in. So that gives us the current index, and then we have to calculate the new index. And oh my goodness, this took me a long time to work out, because for the sample input, you don't you don't need to do it quite this way. You can just kind of I had some shortcuts that I hadn't thought of. I just checked. So I calculated the new index by taking the current index, adding its value, which might be negative, and then if we were if the result was outside of the list, I would I don't remember what I did, but I certainly didn't do the right thing. So the real important trick to realize was this little bit, because I started out just doing this, right? So I wanted to calculate the new index by just adding it and then doing a modulo on the length of the current order. But the thing to realize is that you're popping an element out, and then you're moving it around a number of times, and it could like wrap around multiple times. But on each round through, there's one less element in the list because you've taken one out that you're then moving around. That's why we have to subtract one. And when we wrap around, that's the thing I mentioned, which was frustrating, to say the least, because realizing that if this had been a -2, I really wish that the sample input would cover all these different cases. But I don't know. Maybe that's part of it. Being able to deal with these slight ambiguities. Because if this had been a -2, moving in left 1 and then 2, it wouldn't end up, pushing 1 and 2 over, but rather it, wraps around and ends up as the final element over here. So that is what we are taking into account here, that if we are moving backwards, if the new index that we calculate is 0, but we are moving backwards, then instead we're going to put it at the end. So that's what we do right here. So we create a copy of the current order, call it new order, We pop the element that we're looking for. We got its index up here, and then we insert it at the new index, and we return the new order. And that means that we can just keep calling shift and pass in the current order, and we get the new current order out, and we just keep doing that until we're done. And that's it. That was it actually for part A. All right, let's take a look at part B, part 2. The Grove coordinate values seem nonsensical. While you ponder the mysteries of ELF encryption, you suddenly remember the rest of the decryption routine you overheard back at camp. First, you need to apply the decryption key. 811,589,153. Multiply each number by the decryption key before you begin. This will produce the actual lists of numbers to mix. Second, you need to mix the list of numbers 10 times. The order in which the numbers are mixed does not change during mixing. The numbers are still moved in the order they appear in the original pre-mixed list. So if -3 appears fourth in the original list of numbers to mix, -3 will be the fourth number to move during each round of mixing. Each round, yeah. So we use the same order every time we go through it. And yep, this is just using the example above. These are much bigger numbers and shows what happens after each round of mixing. Okay, and the Grove coordinates can still be found in the same way. Here, number 1000 is this, and 2000 is this, and 3000 is this, and then we add them up, and that gives this. So that's it. So the difference is multiplying every number by this really big number and doing 10 rounds of mixing. And that means that part B is the same function, just do stuff, except with a multiplier and more than one round. And yeah, I don't think we need to go through it, right? Same thing, original order, current order, and then we do the same thing, just except 10 times, always using the same original order, that never changes. Where is it? Oh, there. Yeah, we multiply with the multiplier. So in the original order, which is the encryption key. And yep, that's it. Those were my numbers. Yeah, so that was day 20. Wasn't too bad. I didn't solve it live because I'm still fighting jet lag real bad. So that wasn't happening, but here we are. We got through it, and yep, that was day 20. I hope you could. I hope this helped or was helpful at least a little bit. If you have any questions or comments, you just leave them below. If you enjoyed this, you like and subscribe, and I will see you tomorrow.